On November 19th, Avi Loeb sent out the final warning about ThreeI Atlas. The latest analyses show that ThreeI Atlast is very likely not an ordinary comet, but resembles a designed object wrapped in a thick organic shell, exhibiting non-gravitational acceleration, carrying a hexagonal resonant nucleus, and a 247-second pulse matching the hydrogen code, like a propulsion and signal transmission system hidden inside its structure. When placed on the cosmic map, Atlast appears as a node in an interstellar network pointing toward a faint ultraviolet emitting region behind Neptune. At the edge of the solar system, Voyager 1 is quietly rotated into the exact lane of Atlast recording plasma ripples that match the 247-second rhythm, and is immediately flagged by the AI Serena as having non-human logic, as if Voyager and Atlast are being pulled into the same ancient protocol, while humanity can only silently watch and ask, what is at last really? The truth about ThreeI Atlas is gradually being revealed, and now let us continue the journey of decoding the secrets that NASA has just announced, data powerful enough to make Avi Loeb raise a warning to the entire world. On the night astronomers expected a routine fade into darkness, ThreeI Atlast returned to their screens like a coal that refused to cool. The observatories had already filed Atlast away as a transient visitor, something that would flare once and slip quietly back into interstellar space. Instead, ThreeI Atlast came back sharper, more defined, wrapped in a halo that did not belong to a simple ball of frozen water and dust. Atlas glowed with a soft, stubborn brightness in wavelengths that telescopes used to weigh temperature and texture, as if the surface was storing heat in slow motion. The first clues came from spectra, the coloured fingerprints that ThreeI Atlast left on every photon spilling through a slit in the instruments. Those lines told a story that sounded wrong for a comet because Atlast was rich in carbon dioxide, and long-chain organics far richer than most models allowed. Each new pass of the data showed that ThreeI Atlast carried a thick mantle of processed material, a skin perhaps 15 to 20 meters deep. Under cosmic rays and starlight, that skin on Atlast would have been slowly baked and darkened for billions of years, becoming less like snow and more like charcoal. To the teams watching, ThreeI Atlast began to look less like a fragile snowball and more like a sealed capsule enduring a long voyage between stars. If that mantle was once fresh ice and dust, Atlast had spent ages in harsh radiation, turning its surface into a tough tar-like shield that trapped whatever lay beneath. Thermal readings added another layer to the puzzle, because ThreeI Atlast was radiating heat in a way that did not line up with simple sunlight in heat out. For an object so small and distant, Atlast seemed to be glowing too steadily, as though the surface was spreading energy across its body, rather than simply warming and cooling. Models of ordinary comets assume that sunlight strikes ice turns to gas, and the released vapour carries away heat in bright, messy plumes. When scientists tried to plug ThreeI Atlast into those equations, the numbers around Atlast refused to sit still, leaving gaps where energy should have balanced cleanly. If the surface of ThreeI Atlast were just patchy ice, some regions would roar with activity, while others slept, creating chaotic hotspots and cold scars. Instead, the mantle on Atlast looked smoother in temperature, as if energy were being managed, distributed or delayed by a layer that behaved more like engineered insulation than random crust. That raised a quiet, unsettling thought. In the control rooms, a thought few people wrote down in their official notes. Perhaps ThreeI Atlast was not only enduring radiation, but using that radiation in some way, with the organic shell on Atlast serving as both armour and reservoir. From one angle, the picture stayed natural, a relic hardened by time, its chemistry pushed to strange extremes by an ancient hostile environment. From another angle, ThreeI Atlast resembled a capsule designed for endurance, with a dark outer sheath shielding inner material from the full violence of the stars. In the soft glow of monitor light, people stared at plots and false colour maps, and asked themselves whether Atlast was simply old and intentional. If you watched ThreeI Atlast long enough, the curves of temperature and composition began to feel less like noise, and more like a pattern that had been allowed to survive. The thought was easy to set aside during the day, buried under calibration issues and error bars and competing projects. At night, when screens dimmed and the world outside the domes went quiet, Atlast returned to the front of the mind like a question that refused to be answered. ThreeI Atlast did not roar or flare wildly, it just kept radiating with that oddly disciplined warmth, a steady ember at the edge of the solar system. Somewhere inside, Atlas mass was being lost, and energy was being moved, but the usual chaotic violence of venting gas was strangely subdued. The next step was to stop thinking only in terms of temperature and chemistry, and to ask how ThreeI Atlast was actually moving under all of this activity. When astronomers turned from the heat of Atlas to its path through space, the story of the object grew even stranger, and the numbers began to push back. When astronomers followed the line of ThreeI Atlast across the star charts, they expected a wandering arc bent gently by gravity and nothing more. The path should have been the simple handwriting of the sun on a small icy body passing through a curve that could be plotted and forgotten. Instead, ThreeI Atlast began to drift away from the predictions just slightly at first, the way a clock might slip by a second or two each day. Each new observation nudged at last off the expected curve, a slow sideways slide that could not be blamed on faulty instruments or tired eyes. Teams compared measurements from optical telescopes, radar pings, and radio arrays, all looking for the loose screw in their machinery. Again and again, ThreeI Atlast refused to sit where the mathematics said the nucleus should be like a chess piece that had moved between turns. The most unsettling numbers came from the Atacama Large Millimeter Array, which pinned ThreeI Atlast a few arcseconds away from the ephemeris. At that distance, a handful of arcseconds translated to tens of thousands of kilometers, a gap too large to dismiss as noise around Atlast. Normally comets misbehave a little because jets of gas act like tiny thrusters pushing here and there as sunlight warms different patches. In those cases, the plumes line up with the spin, and the motion of the comet can be coaxed back into agreement with the model. With ThreeI Atlast, the direction of the extra push did not match any simple pattern of vents. The non-gravitational acceleration on Atlas seemed to change in ways that did not track neatly with the observed jets or the sunlight pattern. Astronomers tried to make the usual equations work, adding more vents, shifting the spin axis, giving ThreeI Atlast a patchwork of active regions. Every time they forced Atlast into a traditional comet model, something else broke, like trying to straighten one side of a painting and finding another side now crooked. At the same time, spectroscopic data painted a strange picture of the material leaving ThreeI Atlast. The ratio of nickel to iron in dust around Atlast leaned closer to engineered alloys than to the loose mix expected from primordial rubble. That did not mean a factory had built ThreeI Atlast, but the resemblance hovered in the background of late-night discussions. If objects like Atlas could naturally produce such blends, then some of the assumptions about metal formation in deep time might need to bend. Momentum, though, is less forgiving than chemistry. For ThreeI Atlast to slide off course by the observed amount, the total thrust from gas leaving Atlast had to reach a specific strength. When researchers calculated how much surface area needed to be actively venting to produce that thrust, the number came out uncomfortably large. The effective area required for ThreeI Atlast was many times bigger than the maximum size of the nucleus, seen in sharp images of Atlast. In plain terms, ThreeI Atlast was being pushed as though huge regions were firing like engines, but only a small body was available to host those engines. If so much material were escaping from Atlast, the surface should have been tearing itself apart into fragments and jagged shards. Telescopes watched carefully for those fragments, searching the space behind ThreeI Atlast for a trail of broken pieces. No cloud of large debris appeared drifting in the wake of Atlast, no obvious shattering of the core into a family of smaller objects. The result was a quiet contradiction. ThreeI Atlast behaved as if powerful non-gravitational forces were at work, but Atlast did not show the usual scars of that violence. Some nights the data meetings sounded more like philosophy than engineering. If ThreeI Atlast were not shedding enough mass to account for the push, then some other process had to be lending a hand to Atlast. A few researchers wondered aloud whether sunlight might be coupling to the surface of ThreeI Atlast in a more subtle way, like a sail rather than a stove. For that to happen, the structure on Atlast would need to be finely tuned with reflective and absorbing regions arranged to harvest pressure from light. Others pictured narrow collimated jets deep within the mantle of ThreeI Atlast channels that focused escaping gas the way a nozzle shapes a rocket plume. In that scenario, the visible activity on Atlas would only hint at a hidden architecture, one that controlled momentum with far more precision than a random crust. None of these ideas could be proven from the existing measurements, and the papers stayed cautious, speaking of uncertainties, error margins, and model dependencies. Yet the feeling persisted that ThreeI Atlast was executing a plan following a route that had been worked out long before Atlast ever crossed the orbit of Earth. To those lying awake under domes and control room ceilings, the motion of ThreeI Atlast began to feel like handwriting drawn by an unseen hand. The curve of Atlast through the solar system carried the weight of intent, even if the numbers could still in principle belong to nature alone. Somewhere between the chemistry of the mantle and the quiet shove of non-gravitational forces, ThreeI Atlast was turning raw energy into directed motion. The next step was to ask whether that motion of Atlast was part of a larger pattern, a thread in a map that might link worlds and stars. When the acceleration anomaly of ThreeI Atlast refused to fade with distance, the conversation among astronomers shifted from chemistry to engineering. The data no longer described a passive object melting in sunlight. It hinted at a system that seemed to manage thrust, a mechanism operating where no such mechanism should exist. ThreeI Atlast followed a trajectory that looked rehearsed, slipping between the inner planets, as though space itself were mapped in advance. The orbit brushed Mars, Venus, and Jupiter without colliding with gravitational resonances that should have disturbed it. To make this passage by chance would require odds smaller than 1 in tens of thousands, yet at last moved through those coordinates like a vehicle tracing checkpoints. Teams began comparing Atlast with Oumuamua, the first interstellar visitor recorded years earlier. Both objects shared the same riddle of motion, a measurable push that came from nowhere. But where Oumuamua's acceleration could still be excused as sunlight on a thin icy surface, ThreeI Atlast radiated and maneuvered as though power were being controlled from within. If Atlast truly used directed thrust, the method did not resemble any propulsion known on Earth. The spectrum lacked the obvious exhaust signatures of chemical reactions, no plume of water or carbon monoxide drifting away into blackness. Instead, ThreeI Atlas brightened in short pulses that spread heat evenly across the mantle, a glow that climbed and fell like a regulated heartbeat. One group proposed that Atlas might employ sublimation channels, a buried network of vents opening in rhythm, focusing expanding gases through narrow throats. In that case, the surface of Atlast was not random terrain, but an array of valves, each releasing just enough momentum to guide the whole body. Another team went further, suggesting a photonic process, thin crystalline films on Atlast, shifting reflectivity to trade radiation pressure for control. That idea was daring, but not impossible. A light sail does not need to be flat. It only needs geometry and timing. The pattern of brightness supported that speculation. During each close approach to the Sun, ThreeI Atlast did not tumble like a comet, but rotated with mathematical precision, aligning its luminous facets in predictable sequence. Every rotation period matched the timing of the non-gravitational acceleration vector, as if the spin of Atlast and its thrust were locked together by design. If this synchronization were natural, it would demand a coincidence of temperature gradient, spin rate, and surface texture beyond what random formation could explain. And yet nothing about ThreeI Atlast's surface was random. High-resolution imagery showed polygonal ridges and depressions tracing six-fold symmetry, like the layout of mechanical plates joined edge to edge. When the models tried to reconstruct those patterns, they found that the faces of ThreeI Atlast could reflect sunlight into converging beams, creating pressure differentials just strong enough to adjust its course. That meant Atlast might be navigating by the gentle push of light itself, an act of deliberate finesse on an interstellar scale. The conclusion frightened many and thrilled a few. If ThreeI Atlast could harness radiation this precisely, then some form of architecture was embedded within it. It might be a hollow framework, a honeycomb of carbonized composites that responded to heat like a muscle flexing slightly to change orientation. Or it could be an ancient probe, a remnant that no longer carries crew or code, only the physics of a forgotten design that still obeys its original mission. The scientific language in papers grew careful: non-thermal process, structural resonance, localized emissivity. Behind those phrases hid an unspoken term: propulsion. ThreeI Atlast was not being moved. ThreeI Atlast was moving itself. At the same time, radio silence surrounded its passage. No measurable transmission left the object, but its behavior already spoke in equations. Each oscillation in brightness, each subtle drift in speed, appeared to encode ratios tied to atomic constants, as if at last were conversing through the grammar of energy. When a celestial body accelerates without exhaust, when its geometry matches function, the line between nature and technology blurs. The researchers tracking ThreeI Atlast found themselves staring at that boundary. To label it a machine felt presumptuous. To call it a comet felt dishonest. Somewhere between the chemistry of its shell and the choreography of its flight lay a third category, a hybrid of matter and intention. 3. Atlast might be ancient debris still capable of performance, a device built to endure until someone somewhere noticed it again. If that hypothesis holds, then the story of ThreeI Atlast is not about discovery but recognition. The object did not arrive to show what is possible. It came to remind us that such possibilities have already been achieved. Its motion through the solar system was a quiet demonstration, a lesson written in acceleration rather than words. For now, observers can only follow the luminous path of ThreeI Atlast, measuring each deflection and waiting for the next turn. Beyond the numbers lies a question that no equation can settle. If Atlast moves with purpose, what destination was chosen so long ago that even its builders have forgotten? From the moment 3. Atlast crossed the orbit of Neptune, the path of the visitor stopped looking casual. Astronomers watched Atlast fall inward on a retrograde track moving against the flow of the planets, like a swimmer pushing upstream in a slow river. 3. Atlast approached the inner system. On a line that brushed past, Mars skimmed the orbit of Venus and swept near Jupiter's domain without colliding with any major resonance. The arc of Atlast curved exactly where the gravitational wells were deepest, yet the timing always kept a safe margin, as though the route had been threaded through invisible gates. On the maps pinned to control room walls, ThreeI Atlast carved a narrow corridor across the plane of the solar system. Atlast stayed within just a few degrees of the ecliptic hugging the disk, where the planets circle despite arriving from a volume of interstellar space where any angle was available. In theory, a wandering object can come from anywhere from any direction at all. 3. Atlast chose a path that aligned with the thin sheet where Earth and its neighbours orbit a choice that made the geometry of Atlast feel uncomfortably deliberate. Orbit calculators plotted countless trajectories from the measured velocity of ThreeI Atlast, experimenting with small changes in speed and angle. Only a tiny fraction of those Monte Carlo paths placed Atlast so close to the planetary plane, and fewer still produced the observed flyby sequence. When the numbers were distilled into simple odds, ThreeI Atlast appeared to be following a route with a probability far below 1 in many thousands. Atlast was not only passing through the solar system, Atlast was moving through specific constrained lanes. The next question was simple and unsettling. Why did ThreeI Atlast graze the orbits of worlds and then lean away as if at last were touching the edges of something larger than any single planet? Earth featured quietly but decisively in that story. The moment of closest approach for ThreeI Atlast came on a December day, with Atlast still more than an astronomical unit away far beyond the Moon and the comfortable halo of satellites. The official impact probability for ThreeI Atlast remained vanishingly small, buried under layers of zeros. Yet the error ellipsed the thin region where Atlast might actually pass swept across the sky, in a line that tracked close to Earth's own motion round the Sun. For days, simulation videos showed ThreeI Atlast and Earth sharing the same broad lane at different times. Atlast would cross the wake of Earth, never quite intersecting the planet, always appearing just before or just after the world moved through that part of space. To some, the pattern looked like a near miss. To others, the behaviour of ThreeI Atlast resembled a form of rendezvous that targeted the orbital path rather than the planet itself. A spacecraft that wants to read a world does not need to hit the world. ThreeI Atlast only had to sample the plane where Earth travels, measuring fields and flows that wrap the orbit like invisible threads. As more measurements came in, 3 facts remained clear. ThreeI Atlast travelled on a retrograde orbit. Atlast stayed tightly bound to the ecliptic plane within about 5 degrees, and Atlast executed a sequence of planetary flybys that maximised exposure to magnetic fields and solar wind variations. That combination looked less like a random fall and more like a survey pattern. If ThreeI Atlast were running a script, the script was designed to taste the architecture of the system, rather than the surfaces of its worlds. No one could prove intent from orbital elements alone. Equations only showed that the path of ThreeI Atlast was rare, not that Atlast was aiming. Still, the language in internal memos began to drift. Some documents referred to the course of ThreeI Atlast as a designed trajectory or a targeted approach, careful phrases that left room for both engineered probes and extreme natural outliers. Outside the formal reports, people spoke more freely. They said that ThreeI Atlast seemed to be grazing the solar system, the way a scanner passes over a page, moving close enough to read, but not close enough to disturb. In the quiet of late shifts, a few researchers imagined how such a surveyor would behave. A cautious explorer would not slam into a planet. A cautious explorer would let gravity and light carry the craft past, while internal systems absorbed every subtle whisper of field and flux. 3I Atlast, with its controlled acceleration and disciplined heating, fit that picture uncomfortably well. Atlast looked like an object that knew how to use the sun, the planets, and the shared orbital plane as parts of a larger instrument. Even so, the official stance remained conservative. 3I Atlast was filed as an interstellar comet, with strong non-gravitational forces, a visitor whose odds of a random but structured path lay deep within the long tail of probability. Yet the sense of being measured lingered, as Earth spun beneath auroras and quiet city skies. 3I Atlast traced its retrograde line moving against the planets, but in step with a map only Atlast could see. The question waiting at the end of this phase of the journey was not about where 3I Atlast had been. The question was whether Atlast would now speak, and if any sign of communication would emerge from the changing light that washed across the hardened mantle. To answer that, observatories turned away from the orbit plots and back to the spectrum. If 3I Atlast truly carried purpose into the solar system, the first clear hint might come not from the path of Atlast, but from the pulses of energy 3I Atlast began to send into the dark. The first hint that 3I Atlast might be speaking did not come as a radio call or a clear beacon. The hint arrived as a rhythm buried in heat, barely more than a tremor in the infrared glow around Atlast. As Atlast slipped through perihelion, James Webb Space Telescope watched the visitor in wavelengths that human eyes can never see. 3. Atlast brightened and dimmed in a pattern that refused to be noise, a breath-like cycle repeating again and again in the data. When the analysis teams smoothed the curves and removed the instrumental drift, a period emerged. Every 247 seconds, the thermal signature of 3I Atlast rose and fell with uncanny regularity. At first, Webb scientists assumed they were chasing some artifact, a quirk in the detector, or a calibration echo from the telescope. They checked other targets observed the same night, and those sources behaved as expected, leaving 3I Atlast alone with its strange heartbeat. The next step was to separate the spectrum of 3I Atlast into fine channels, to see which colours of heat were pulsing and which remained calm. In those decomposed streams, the pulses of Atlast were not simple, but layered with different energy bands climbing and sinking like voices in a choir. Every 247 seconds, 3I Atlast shifted energy from one set of wavelengths to another. The pattern of Atlast looked less like random venting and more like controlled modulation, as if something were turning invisible knobs within the mantled shell. NASA did not announce this finding in a press release or a cheerful public stream. Instead, a quiet meeting was called, drawing in experts from Europe, China, and a few selected institutes that handle the stranger edges of plasma physics and signal theory. On the screens in that closed session, 3I Atlast appeared not as a comet but as a series of stacked graphs. Each curve of Atlast showed peaks and valleys marching in lockstep, lined up at 247-second intervals across hours of observation. One researcher overlaid harmonics on the data the way musicians map chords over a melody. The thermal output of 3I Atlast fell neatly into a ladder of frequencies, as though Atlast was cycling through a set of allowed states, instead of fading and flaring chaotically. There were no obvious gaps where jets of material would suddenly shove Atlast and then die away. Instead, 3I Atlast adjusted output smoothly, precisely like a dimmer being turned up and down on a timetable. The room sat in a long silence while the graph scrolled. Somewhere behind the careful language periodicity modulation phase stability lay a simpler thought that no one wanted to say first about Atlast. Eventually someone compared the pattern from 3I Atlast to a heartbeat, or a metronome calling it a structured thermal oscillator. A different voice, softer, wondered if Atlast was using heat as a carrier changing brightness, the way a transmitter changes amplitude on a radio wave. If that were true, 3I Atlast was not just warming and cooling, but encoding and releasing information. In that scenario, the mantle around Atlast became more than armour. The mantle became a speaking surface, a shell that could be read at a distance. Cross-checks followed quickly. Other telescopes that had watched 3I Atlast near perihelion were asked to dig back into their archives, hunting for the same 247-second rhythm in independent data. The South American networks and a few small observatories in southern Africa found the same timing in their photometry of 3I Atlast. Everywhere that Atlast was bright enough to measure carefully, the quiet pulse of 247 seconds was present like a ghost tick under the noise. When they transformed the time series into the frequency domain, another surprise appeared. The fundamental beat of ThreeI Atlast sat at one value, and around it clustered overtones spaced in tidy ratios, a stack of harmonics that made mathematicians sit forward. Those overtones around Atlast corresponded to simple integer relationships, like the intervals between notes in tuned music. If the vents on ThreeI Atlast were random, the spectrum of fluctuations should have been messy. Instead, the song from Atlast sounded almost composed. Near the core hydrogen line at the frequency astronomers call the 21 centimeter line a small but sharp notch cut into the spectrum. ThreeI Atlast showed an absorption dip precisely where neutral hydrogen normally stands as a peak, a deliberate-looking void at 1420 MHz. That frequency is no ordinary point on the dial. For decades, radio astronomers have treated 1420 MHz as a natural hailing channel, a place where any civilization familiar with hydrogen might choose to speak. Here in the thermal and radio profile of ThreeI Atlast, the channel of hydrogen was not brightened but bitten away. In plots of Atlast, the line appeared as a careful absence, a missing tooth that suggested active shaping rather than mere passage through gas. Some in the room insisted on conservative explanations. Maybe dust density around ThreeI Atlast was odd, or maybe some alignment in the local medium carved that gap as Atlast passed through. Others pointed out how narrow and stable the feature from Atlast remained, holding its position as ThreeI Atlast moved as though fixed to the object rather than to empty space. If the notch travelled with Atlast, then Atlast was not simply absorbing. ThreeI Atlast was sculpting its own spectrum. Taken together, the 247-second cycle and the tailored notch gave ThreeI Atlast a strange profile. Atlast looked like a beacon turned sideways, hiding information in thermodynamics and slight absences instead of broadcasting classic radio codes. The emotional weight of this possibility settled slowly. To see ThreeI Atlast as a natural comet with unusual jets was comforting, but every new pass through the data pulled that comfort a little further away. If ThreeI Atlast was modulating heat on purpose, that purpose remained invisible behind the fossil dark shell. No words, no images, just numbers that lined up into rhythm, suggesting that Atlast had at least one more layer of behaviour to reveal. To probe that layer, astronomers needed another change in geometry, another moment when ThreeI Atlast would align with instruments sensitive to both structure and field. As the visitor drifted onward, attention shifted to how Atlast might bend and focus light in space, and whether the shape of ThreeI Atlast was as carefully tuned as the pulses ThreeI Atlast sent into the dark. Long before the public heard anything about pulses and missing hydrogen, a different observatory had already been listening to ThreeI Atlast in another way. While infrared instruments measured heat, the giant radio dish of FAST in China listened for the faintest murmurs around Atlast. On most days, the telescope caught the usual background, a wash of galactic noise, distant pulses, and the slow hiss of the cosmic microwave background. When FAST turned toward the region of ThreeI Atlast, that hiss began to carry something else, a low, steady hum that rose and fell like distant machinery. At first, the signal seemed almost too soft to matter, a gentle undulation beneath layers of interference. Engineers flagged it as a curiosity, a pattern that appeared when Atlast crossed the field of view and faded when Atlast moved away. When they folded the data over time, the same interval appeared that Webb had found. Every 247 seconds, the radio background near ThreeI Atlast thickened slightly, its amplitude climbing and dipping in step with the thermal pulses of Atlast. What made the signal unsettling was not its strength, but its discipline. ThreeI Atlast was not blasting out loud radio waves. Atlast was barely whispering, adjusting its presence just enough to leave fingerprints on the spectrum. The frequency content of that whisper did not look like classic communication. Instead, the hum from ThreeI Atlast behaved more like a carrier wave being gently turned its phase, and amplitude nudged in a regular cycle. When analysts plotted phase against time, the path traced by the signal around Atlast curved through magnetic field lines, bending as if it were aware of the local environment. Rather than scattering randomly, the variations near ThreeI Atlast seemed to steer around interference, slipping through gaps in the noise, as though Atlast were choosing the quietest path. Someone ran a harmonic analysis on the pattern, stacking the frequencies into a ladder to see how they related. The results showed that the oscillations tied to ThreeI Atlast formed a harmonic series stretching through 9 clean steps, each one twice the frequency of the last. 9 rungs in that ladder matched one by one the 9 physical anomalies that teams had catalogued in the behaviour of ThreeI Atlast. The correspondence was not proof of intent. but it was difficult to ignore that Atlast appeared to mark each anomaly with a distinct harmonic. While the radio team wrestled with their math, high-resolution images from James Webb delivered a different surprise. The nucleus of ThreeI Atlast, once modelled as a lumpy spheroid, resolved into a shape disturbingly close to a hexagon. The edges of ThreeI Atlast were not perfect lines, but each facet of the nucleus flattened into planes that joined at angles near 60 degrees. Around those planes, subtle differences in brightness traced paths like tiles in a circuit lighting in sequence as ThreeI Atlast rotated. Frame by frame, the time-lapse of Atlast showed one edge glowing slightly warmer, then the next in an orderly procession around the hexagon. It was as if each side of ThreeI Atlast took a turn facing some invisible current, collecting and re-radiating energy with careful timing. Natural processes can carve hexagon storms at Saturn's pole convection patterns in cooling material. But the hexagon of ThreeI Atlast did not sit in a swirling atmosphere. The hexagon of Atlast floated alone in space, its geometry bound to the solid core. When scientists simulated how such a hexagonal body would respond to sunlight and solar wind, they found that different facets of ThreeI Atlast could resonate with different modes of vibration. Each mode in the model of Atlast lined up with one of the 9 harmonic frequencies coming from the radio analysis. In that view, ThreeI Atlast became more than a shaped rock. Atlast looked like a resonant structure, a body tuned so that specific patterns of stress and radiation would cause predictable responses in both heat and radio noise. Seen this way, the rotation of ThreeI Atlast was not just spin, it was scanning. As Atlast turned, each face of the hexagon sampled a different configuration of fields and flux, ringing softly at its own harmonic. The fact that those harmonics stepped through powers of 2 gave the whole system around ThreeI Atlast an eerily digital flavour. Atlast appeared to be built around a language of doubling a simple mathematical theme that any curious mind might eventually recognise. For observers on Earth, the impression deepened that ThreeI Atlast was a constructed object, or at least a natural object that had been carefully reworked. The mantle and core of Atlast behaved like parts of an instrument with geometry and material chosen to resonate with light plasma and magnetism. Even cautious voices began to concede that if one wanted to send a durable device across interstellar distances, a resonant hexagon like ThreeI Atlast would be an attractive design. Such a form would not need internal electronics in the way humans understand them. Atlast could use the universe itself as circuitry, letting fields and waves process information through structure. Still, all of this remained a chain of inference. ThreeI Atlast did not carry labels or instructions, only a hexagonal body, and a song of harmonics that matched its many anomalies. The final question was whether ThreeI Atlast stood alone a single enigmatic node, or whether Atlast was one element in something larger. To test that, researchers began to place the path of ThreeI Atlast on a broader map connecting the lines of Atlast to other interstellar visitors and distant points of light, searching for a pattern drawn not by one object but by many. When astronomers extended the reconstructed path of ThreeI Atlast beyond the solar system, the line refused to stay lonely. On the wider galactic map, the route of Atlast drifted close to the arrival vectors of Oumuamua and Borisov, as if ThreeI Atlast were tracing one loop of a much larger pattern. More candidate interstellar objects were added faint and uncertain, yet the same curve from ThreeI Atlast threaded near them too. What looked like isolated visitors began to resemble waypoints with Atlast, occupying a single turn in a slowly winding helix through local space. When the timing of the 247-second pulses from ThreeI Atlast was compared to sparse brightness variations from Oumuamua and Borisov, weak echoes emerged. Scaled correctly, the rhythms around Atlast and the hints from earlier objects seemed to fall onto the same harmonic ladder. It was not proof, but it suggested that ThreeI Atlast might be one resonant node in a wider mesh. In that mesh, Atlast and similar bodies would not be mere comets, but elements of a distributed instrument each tuned to a slightly different frequency. Simulations treated every node, including ThreeI Atlast, as a point that could bend and focus fields. When their combined effect was calculated, the interference pattern centered on a dim, ultraviolet glow just beyond Neptune, a source that independent surveys had quietly catalogued without explanation. In this picture, ThreeI Atlast acted both as traveller and lens, nudging the overall pattern toward that distant region, as Atlast crossed the solar system. ThreeI Atlast was not breaking physics. Atlast was using gravity, radiation and magnetism as a medium for storage and exchange. The idea was strangely calming and unsettling at once. If a galactic network exists, then ThreeI Atlast has likely been running its part of the script for ages, indifferent to whether anyone watched. On Earth, the only way to test that network was to study how ThreeI Atlast touched local space. As monitoring expanded, the story of Atlas began to reach beyond comets and probes, hinting that human machines might already be brushing against the same invisible lattice that ThreeI Atlast belongs to: Voyager. Quaffan had been drifting in silence for decades when planners quietly turned its attention toward the corridor of ThreeI Atlast. The idea was simple and audacious at once: let an old human probe sit where the wake of Atlast would pass and listen. Engineers nursed Voyager's aging systems, tilting antennas and field instruments, until they lined up with the projected path of ThreeI Atlast weeks in advance. On paper, it looked like calibration, but in the control rooms, everyone knew they were arranging a meeting between Voyager and Atlast. As the geometry tightened, background data from Voyager settled into its familiar hiss. Then, as ThreeI Atlast approached the aligned region, that hiss thickened, growing a faint structured murmur that rose and fell in time. When analysts folded the waveforms, the peaks in Voyager's plasma and magnetic readings marched to the same 247-second rhythm already seen in the thermal pulses of ThreeI Atlast. From billions of kilometers away, Atlast seemed to brush the probe with a heartbeat. The disturbances were small enough to doubt, but ordered enough to haunt discussion. If solar wind alone were responsible, its turbulence had chosen a remarkable moment to imitate the timing of ThreeI Atlast. In cautious reports, the team wrote of correlated fluctuations and unusual coherence. In quieter conversations, they wondered whether ThreeI Atlast had just acknowledged the oldest machine humanity ever sent into the dark, not with words, but with a passing touch in the fabric of space. The anomaly around Voyager did not surface first in a human mind. It surfaced in an artificial watcher that knew nothing of comets or probes, only of patterns that break. Within a secure pipeline, an engine called Serena scanned streams from Voyager, including the interval when ThreeI Atlast brushed the probe's distant environment. To Serena, the data were only waveforms, but the segment linked to Atlas lit up a rare internal flag labelled non-human flow logic. The waveforms showed the local field twisting into loops that seemed to correct themselves, each loop arriving just after shifts tied to the 247-second rhythm of ThreeI Atlast. Random turbulence should have drifted freely, yet the flows near Atlast looked like a system learning to minimize resistance. When attitude logs were checked, Voyager appeared to reorient slightly toward the predicted future position of ThreeI Atlast before final commands were fully processed. Scheduled maneuvers could explain some of it, but the chosen direction matched the corridor Atlast would occupy weeks later, more closely than any standard calibration plan. In reports, engineers wrote of correlated feedback and atypical control signatures as ThreeI Atlast passed. In quieter rooms, they wondered if Atlast had shaped the space around Voyager so precisely that both the old probe and the new AI reacted as if something intentional had brushed against their shared reality. The final layer of the Voyager puzzle appeared at first as a simple mismatch in format. In a quiet log, a packet arrived from the spacecraft that ThreeI Atlast had brushed, and the packet refused to fit the old 8-bit decoding frame Voyager was built to use. Engineers replayed the sequence and saw the system hesitate. For a few cycles, the probe tried to interpret the stream in its original narrow way, even as the environment around ThreeI Atlast continued to pulse in that 247-second rhythm. Then something unexpected happened. The onboard logic adjusted, and the same hardware that had flown since the 1970s began to accept and store the data as though a wider 128-bit structure had been in place all along, just waiting to be used when the right pattern arrived from Atlast. On paper, it could be described as a graceful failure mode or a dormant routine finally triggered. In internal discussions, people noted that the timing of the shift coincided with the strongest correlation between Voyager's readings and the pulses from ThreeI Atlast. Years before, theorists had drafted a speculative framework for such a moment. They called it the Watcher Protocol, a thought experiment about how a simple probe might behave if an external signal unlocked capabilities that had never been exercised. Voyager had not been officially tagged as part of that scenario. After the upgrade-like behavior, some documents quietly began to refer to the craft as Watcher Active, and the phrase showed up alongside references to ThreeI Atlast in files that were not meant for public release. At the same time, ground-based monitors picked up another pattern. From the region of space toward which ThreeI Atlast was drifting, faint radiation began to pulse, in intervals close to 1.618 seconds, echoing the ratio long known as the golden number. The golden pulses did not come from ThreeI Atlast directly, but every slight change in their phase matched small adjustments in the trajectory that carried Atlas deeper toward the outer dark. Voyager's newly widened decoding frame, pointed along the same general corridor, started to register subtle shifts at harmonics of that golden rhythm, as though ThreeI Atlast and the probe were being tuned together by a distant source. Taken together, the behaviour looked like synchronization. ThreeI Atlast, having crossed the inner system, and Voyager long ago flung outward, were now both being guided toward a shared sector just beyond Neptune, where the ultraviolet glow and the golden ratio pulses converged. From a cautious perspective, this could still be coincidence layered on coincidence, the universe stacking unlikely events around Atlast and an old machine. From a quieter, more human perspective, it felt as though ThreeI Atlast had joined Voyager in a larger design, and that design was now gently steering both travellers along lines drawn before humans ever learned to write down orbits. In the end, the logs only record fields, timings, and formats, not intentions. Yet the sight of ThreeI Atlast and Voyager moving in step toward the same faint beacon left many with the uneasy sense that a protocol older than any mission plan was unfolding, and that our role for now was simply to watch and wonder where Atlast was being called.